This video tutorial is the third part of a three-part lecture series on geometric optics. Its emphasis is on the different types of lenses. Such questions like, how do we know if a given lens is a converging lens or a diverging lens? There are two types of lenses. The first one is what we call converging lenses. And there are three examples illustrated here. The first one is called a concavo-convex because it is made up of two surfaces. One is a concave surface and the other is a convex surface. Now the second one is called a plano-convex because it's made up of a plane surface and a convex surface. And the third is called a double convex lens because both surfaces are convex. We also have diverging lenses, and here are the three examples. The first one is called a double concave because both surfaces are concave. The second example is called plano-concave because it is made up of a plane surface and the other surface is a concave surface. And lastly, the convexo-concave is made up of a convex surface and a concave surface. Alright, so to summarize the different types of lenses, you may have noticed that for converging lenses, uh, the geometric center of that lens is thicker than or when compared to the edges, while a diverging lens is thinner at the geometric center compared to those at the edges. And um, to recap what you just showed earlier, that under converging lenses, there can be what we call concavo-convex, plano-convex, and double convex lenses. And for diverging lenses, common shapes are the double concave, the plano-concave, and the convexo-concave. We can determine the focal length and the type of lens of a given lens using what they call the Lensmaker's equation, whose formula is 1 over f equals quantity n minus 1 multiplied by 1 over r1 plus 1 over r2. So in this formula, small f stands for the focal length of the lens. Small n refers to the index of refraction of the material the lens is made of. And that value of n is usually relative to the surrounding medium. So, for example, the lens is just surrounded by air. It's understood that n is divided by 1.00 because the index of refraction of air is equal to 1.00. But if a given lens is immersed in a given liquid whose index of refraction, for example, is 1.5, right? Then therefore, this small n still has to be divided by the index of refraction of the surrounding medium before 1 is subtracted from it, right? The two r's refer to the radii of the two surfaces. But there are cases when a given lens only has one curved surface because the other surface is a plane. So in which case, we only consider one radius, either R1 or R2. Just like image formation by mirrors and lenses, we also have to follow a certain sign convention. Okay, So uh, if the lens is known to be converging, then the focal length is considered positive. Okay, but if the lens is a diverging lens, then its focal length is negative. The two R's, either R1 or R2, is treated as positive when the surface is convex. Okay, we know that the surface is convex because it is curved outward. Okay, so if the surface is convex, we assign or we consider the radius, either R1 or R2, to be positive. But if the surface is a concave surface, meaning it is curved inward, then we treat either R1 or R2 to be negative. Okay, here is an illustration. So for example, what we have here is a kind of lens whose center or geometric center is thicker than its edges, right? So the surface facing to the left is a concave surface whose radius of curvature can be represented by this green circle whose radius is also represented by R1. And since it is a concave surface, okay, we say that the R value, R1, is considered negative. Now, for the other surface, okay, the one facing to the right is a convex, whose imaginary circle is represented by the red circle, whose radius is represented by R2. And since it is convex, its radius of curvature is treated as positive. For our first example of a problem, we have a meniscus lens which has a convex surface whose radius is 25 centimeters and a concave surface whose radius of curvature is 15 centimeters. The index of refraction is 1.52. Find the focal length of the lens. Is it converging or diverging? Alright, so our solution to this problem is as shown here. Okay, we identify the first radius R1, okay, according to the problem, is a convex surface, okay, whose value of the radius is 25 centimeters. Since it is a convex surface, therefore we assign a positive sign to this radius. And the other radius, which is a concave surface, right, has a value of 15 centimeters. But since it's a concave, then we put here a negative sign for its radius equal to negative 15 centimeters. The index of refraction, of course, is 1.52. We are asked to find the focal length for this meniscus lens. And the formula that we follow is that of the Lensmaker's equation. Substituting the given, okay, 1 over f is equal to quantity 1.52 minus 1. Alright, and then multiplied by the quantity 1 over 25 centimeters minus 1 over 15 centimeters. Okay, uh, notice that this is 1 over f. So after doing our algebra, don't forget to uh, invert your computed value, because that would just be equal to 1 over f. And since we are looking for the focal length f, okay, we have to get the reciprocal. All right, and that is equal to negative 71 centimeters. So using our sign convention earlier, which we said that if the focal length is negative, then the lens is a diverging lens. And as shown in the rough sketch, right? Notice that the surface that is convex, okay, has a greater magnitude for the radius, 25 centimeters, as compared to the concave surface whose magnitude of the radius is only 15 centimeters. So if you're going to draw the sketch for that kind of radius, it will come out like this. All right. Uh, we will have a lens whose geometric center will be thinner than its edges. Right. And that is one physical characteristic of a diverging lens. A lens whose geometric center is thinner than the edges. Therefore, our interpretation for the focal length, since it's negative, when we said it's a diverging lens, also agrees with our sketch for this kind of lens. Our second example, a meniscus lens has a concave surface whose radius is 25 centimeters and a convex surface whose radius of curvature is 15 centimeters. The index of refraction is 1.52. Find the focal length of the lens. Okay, is it converging or diverging? Okay, if you compare this with the first example, okay, they're quite similar except for the fact that we reverse this time the concave surface, which says here has a radius of 25 centimeters, while the convex surface has a smaller radius of 15 centimeters. Earlier, it was the reverse. So we will see what's going to happen. All right, so identifying both the R1 and the R2, okay, we have negative 25 centimeters for the concave surface. Since it's concave, that's why it is with a negative here. And for the other surface, R2, it is a convex and therefore it has a positive sign for the radius 15 centimeters. Again, the index of refraction n equals 1.52. We're looking for the focal length f, and using the the Lensmaker's equation, we substitute. Doing our algebra, we will get this value for the focal length, which is positive 71 centimeters. And our conclusion is that it is a converging lens based on our sign convention. Now, just like what we did earlier in the first example, if we compare the magnitude of our radius, R1, okay, which is a concave surface, it is the one that's longer, okay, than the convex surface. See? So if you're going to draw it carefully, we will arrive at this kind of sketch. Okay? Uh, we have the, what do you call this? The concave surface, the one facing to the left, okay, has a greater radius of curvature. You can imagine its radius of curvature. Okay, like that. While the other surface, the one facing to the right, is a convex surface and whose radius of curvature is lower or smaller than that of R1. R2 is 15 centimeters. So what happens is that the resulting sketch will show a lens whose geometric center is thicker than the edges, right? And our description for such kind of lens where the geometric center is thicker than the edges, we say is a converging lens. So again, our interpretation of the computed focal length, whose sign of the focal length is positive, we said it's a converging lens, also agrees with our rough sketch. Let me now check your understanding after discussing two examples. Let's have this multiple choice question. A meniscus lens made of glass whose index of refraction equals 1.52 has a convex surface whose radius is longer than the radius of its concave surface. Which of the following is or are true about this lens when it is immersed in a liquid whose index of refraction is 1.60? We are looking for one or more answers. Letter A. Its center is thinner than its edges. Letter B. It is a diverging lens. Letter C. Its center is thicker than its edges. And letter D. It is a converging lens. So, the question doesn't give the exact value for the two radii. It only says that the convex surface has a radius that is longer, okay, than the concave surface. So what we are going to do in the next slide is we simply assign values to satisfy this condition in the question. All right, and then do the same thing. We will calculate for the focal length and then recall our sign convention and possibly do a little sketching. Okay, we'll see if which one or more of these choices, okay, is or are correct. All right, so our solution is first we identify the given data for the two radii. We have R1. We just what do you call this? We just assign this following the condition in the question. So for our radius number 1, we have 1.60 centimeters, and this is the convex surface. That's why it's positive. For the other surface, which is a concave surface, we will assign a much lower value for the radius, but since it's concave, we will assign a negative radius. And for the first index of refraction, this is the index of refraction of the lens itself, which is 1.52. And then the liquid surrounding that lens, because the lens will be immersed in this particular liquid whose index is equal to 1.60, right? And we are looking for the focal length. So we will be using, of course, just the same, the formula for the Lensmaker's equation. Okay, and then substitute. By substituting, we have 1 over f is equal to quantity 1.52 divided by 1.60 minus 1. So before you subtract 1, you have to first get the quotient of 1.52 divided by 1.60. And then, after deducting 1, we will multiply it to the difference between 1 over 6 minus 1 over 2. And when you simplify that, all right, remembering to get the, what do you call this, the reciprocal, because we are looking for f, not 1 over f. The value that we will get is a focal length equal to positive 60.6 centimeters. Since it is positive, our conclusion is that it is a converging lens. Okay. Now, if you're going to examine back the magnitudes of the two radii and do the rough sketch, we will come up with this kind of sketch. Okay. It says there that the convex surface is longer Okay, the convex is longer than the concave surface. So the one facing to the left is convex. You can imagine the circle that it defines, right? Whereas the one facing to the right is a concave surface. So its imaginary circle is just about that big, whose radius of course is from the center to the circle. So obviously, our what you call this, our sketch follows, okay, the given condition that the convex surface must be longer in terms of radius, must be longer than that of the concave, right? Meaning, all right, a lens that has a thinner geometric center. Supposedly, okay, supposedly, if a lens has a thinner center, geometric center, it must be a diverging lens, okay, by definition. But why is it that our computed F is positive? So that we came up with our conclusion that it is a converging lens. Okay, a positive focal length, even if the center is thinner. Okay. The reason is that this particular lens is being immersed in a liquid whose index of refraction happens to be greater than the index of refraction of the lens material. So, if you notice our computation, okay, that ratio 1.52 over 1.60 will result to a number that is less than 1, 0.95. So that when we subtract 0.95 minus 1, get we get a negative value, which when multiplied to the sum of 1 over R1 plus 1 over R2, which is also negative, all right, the resulting sign of our focal length is positive. That's why we said it's a converging lens. Okay, our computation is correct. There's nothing wrong with our resulting sign. It really is a positive sign. That's why we interpreted it as a converging lens. Okay, even if in our drawing uh, the geometric center appears thinner than the edges. So this is one rare case where a lens, whose physical appearance appears to be a diverging lens, but when immersed in a liquid, such as this one here, whose index is higher than the index of refraction of the material for this particular lens, okay, will in fact become a converging lens. So that's it. Our answer, therefore, to the question, check your understanding, as given here, is options letter A and letter D. Right? So that ends our discussion for this particular video tutorial. Thank you very much.